Hi all, I am K. Surya, working as Assistant Professor in the Department of ECE at SNS College of Technology. So in this video, let us see about Norton's theorem. So it states that any two-terminal linear network can be replaced with an equivalent circuit which consists of a current source in parallel with a resistor. So in the Thevenin circuit, we will be drawing a voltage source in series with a resistor, whereas in Norton's equivalent circuit, we will be finding out a current source which is in parallel with a resistor. So this is the Norton's equivalent circuit. So here a two-terminal linear circuit is replaced with a current source mentioned as IN drawn in parallel with a resistor RN, and you will be connecting the load across the RN. So next we will see the procedure for Norton's theorem. So in first step you will be considering the circuit diagram by opening the terminals with respect to which the Norton's equivalent circuit is to be found. So in order to find out the Norton's current, first you will be shorting the two open terminals of the above circuit. Then in order to find out the resistance Rn across the open terminals of the circuit, which is done in step 1, you will be eliminating the independent sources and you will be finding out the Norton's equivalent resistance. So your Rn will be the same as your Thevenin's resistance. Then you will be drawing the Norton's equivalent circuit. So for finding out the Norton's current IN, we will be short circuiting the load resistance and then you will be finding out the current. Then in order to find out the Rn, the same way as we did in the Thevenin's theorem, we will be open circuiting the load resistance and we will be short circuiting the voltage source or open circuiting the current source, and you will be looking back the resistance from the point AB to find out the equivalent resistance. So Thevenin's equivalent and Norton's equivalent resistances are the same. So we will see an example. So in this example, you find the Norton's equivalent circuit. So you have to connect the Norton's equivalent circuit to the load and find the current in the 50 ohm resistor. So the first step is across AB, you have to remove the 50 ohm resistance and then you have to short circuit the AB in order to find out the current IN. So it is shown in this figure. So here the current is mentioned as ISS. So you can find out the current by using the mesh analysis. So here you are having 3 loops. So you can write 3 equations and find out the current ISS, which is your current. So you will be getting it as 10.7 amps. Next you want to find out the resistance. So in order to find out the resistance, what you will do is, in this circuit you will be open circuiting AB and then you will be short circuiting the voltage source 50 volts. You will be open circuiting the current source 10 amps. So you will be having only 20 ohms, 40 ohms and 60 ohms. So when you see from the point AB, 20 ohms will be in parallel with 60 ohms. So 20 into 60 divided by 20 plus 60, and the answer you will be adding it with 40 ohms. So you will be getting the answer as 55 ohms. So then you are drawing the Norton's equivalent circuit. So your current is 10.7 amps. So current source is drawn in parallel with the resistance, which is 55 ohms, which is the Norton's resistance, and then your load resistance is 50 ohms. So now you can find out the current through 50 ohms using current division rule, which is total current into opposite resistance divided by sum of the resistance. So it is 10.7 into 55 divided by 55 plus 50. So we will see one more example. So here you have to find out the current through 3 ohm resistor by using Norton's theorem. So here the 3 ohms is the middle resistance AB. So first we will be short circuiting that in order to find out the current, and for finding out the resistance we will be open circuiting AB and then you will be short circuiting both the voltage sources, 24 volts and 12 volts. So first you are calculating Rn here. So you are open circuiting AB, you are short circuiting both the voltage sources. So when you see from the point A, your 6 ohms and 1 ohms will be in parallel. So 6 into 1 divided by 6 plus 1. So you will be getting 0.85 ohms. Next one, you will be calculating the current. So to calculate the current, you will be short circuiting the point AB. So when you short circuit the point AB, you can use current IN is calculated by I1 plus I2, because the current is flowing from negative to positive. So direction of current is shown here. So both the currents I1 and I2 are entering into the point A. So I1 plus I2 will be giving you IN. So you can calculate I is equal to V by R. So I1 is equal to 24 by 6 and I2 is equal to 12 by 1 ohms. So when you add both the currents, you will be getting 16 amps. So your IN is 16 amps and your RN is 0.857 ohms. So this is your Norton's equivalent circuit. So we will be drawing the 3 ohm resistance, which is the load resistance, and you can calculate the current using current division rule, which is 16 into 0.857 divided by 0.857 plus 3. That is total current into opposite resistance divided by sum of the resistance. So your load current will be 3.55 amps. So hope you understood Norton's theorem. So in order to find out the Norton's current, you have to short circuit the point AB and then you have to find out the current through that terminal, and then in order to find out the resistance, you have to open circuit the terminal AB and you have to replace the voltage and current sources by either short circuiting or open circuiting it, and then you will be calculating the equivalent resistance. So we will take up some assessment questions. So the Norton's current is, the choices are short circuit current, open circuit and short circuit current, neither open circuit nor short circuit current. Yes, the answer is short circuit current. Next one is Norton's theorem is true for linear networks. It's not used for non-linear networks. So the answer is linear networks. And the next one is Norton's resistance is found by, yes, the answer is shorting all the voltage sources and open circuiting all the current sources. Thank you for watching this video.